Okay, so this is our third presentation for Chapter 14, Aqueous Equilibrium and Acids and Bases. So now we're talking about equilibrium solution of polyprotic acids. Now this is assuming that these are all weak, right? So the situation where you have the strong acid, H2SO4, sulfuric acid, its first ionization is strong and its second one is weak. That's a special case. But for the most part, when we're talking about these polyprotic acids, all the dissociations are weak. You can also have polyhydroxyl bases. The text does not talk about these, but they would work very similarly if for some reason a base could produce more than one, or accept more than one proton, or somehow produce more than one hydroxyl ion and it was weak, then it would work the same way as what we're going to discuss here. So again, we're making the assumption that these are both weak. When that's true, the first dissociation will always be the strongest, okay? And that's also true even when one of them is strong. In the case of sulfuric acid, the first dissociation is the strongest one. That's a general rule across all sorts of multiple equilibria. When a system, its product will continue into subsequent equilibria, the first one will always be the strongest, meaning it will have the highest value, favor the products much more so, because each subsequent one kind of builds on the last one, and so that the odds of it happening decrease over time as we spread this out, right? So like in order for this to lose the second proton, it has to have already lost the first proton. It's kind of the logic that goes on here. Sometimes both these protons are equivalent, so it doesn't matter which of the two is lost. Sometimes they're not. And so I can identify a specific proton that goes with each of these Ks. That's another thing to also think about. Here we have carbonic acid is a diprotic weak acid, so both of them are weak. It dissociates to form carbonate in the blood, and it undergoes two losses of a proton, so two dissociations. The first one is stronger than the second one. It has a higher equilibrium constant, and then the second one is smaller. So these can vary by many orders of magnitude. Sometimes the second dissociation is so small that it's just irrelevant. And like I say, because of the percent dissociation issues that we talked about in the previous lecture, it turns out that the higher the starting concentration of any of these multiple polyprotic systems, the less the subsequent dissociations matter. So they typically only matter when you have relatively dilute solutions. Then the subsequent equilibria will matter. Okay, so that's another point to keep in mind. Again, sulfuric acid, very large. Because it's strong, they don't really quantify it. I can't really quantify it in water. I can quantify it in other ways and get a number for how strong sulfuric acid is. But if I just put it into water, like what we're talking about, it acts the same as all other strong acids, so I can't really tell it apart. And then the second dissociation is by 10 to the minus 2, so that's pretty strong for a weak acid. Like this would be one where that dissociation, we would have to use the quadratic formula like we were talking about. Like that's a red flag because it's actually pretty strong. So you can see how as a dilute acid, it could act almost like a diprotic acid. But as it gets more concentrated, it acts more like a monoprotic acid. All right, so they say here, because the first dissociation is the strongest acid, the principal reaction is the dissociation of the first proton. And essentially all the H3 plus comes from the first dissociation and then the second subsequent ones. Okay, so sulfuric acid differs from most other ones because it has a very large value for the first one. Yeah, but only a fraction dissociate. Again, we'll look at an example. So here's carbonic acid. So what I'm going to ask you to do subsequently as we move through some of these acid-based problems, when you're asked to calculate a pH, I want you to do the quick and dirty way. Use the cheesy equation that we've looked at before to estimate your pH value right off the bat. As soon as you read the problem, okay? Find your value. Just use the first Ka. Like when you have multiple ones like this, just pick this first Ka, pick this first concentration, plug them in, and calculate it. It's going to turn out that the pH you get is the right answer, okay? We're close enough. Because of the big difference between Ka1 and Ka2, it essentially doesn't contribute at all. Now that doesn't give us all the answers to the problem though. That only gives us this first part, this pH. So if you didn't have time, like you were rushing through a problem, you're at the end of the test, you can't do all of this. And on a test, I generally wouldn't ask you for all this much in a single question anyway. But like, if you could at least get the pH, you could answer this partially, right? And typically, As long as these Ka values are small enough, then this H2SO3 will be essentially the same as its previous concentration. This one will be the same as the if you undo the pH, if you get the concentration, it'll be approximately this answer and this answer. So you can actually get 3 of these answers just from this equation, assuming that this assumption is pretty reasonable. You can get this concentration, which is essentially going to be the same as your starting. This one and the H3O plus will be equal, and they will be the concentration. If you take like 10 to the minus 4.03, that answer will be these two. So you can get most of these concentrations without having to go through all this rigmarole we're going to go through by looking at the problem. And bear in mind that that's possible, and you'll want to do that to start so you have some way to check your answers, even if you do need to go through all this process. Like they have an 8-step procedure here, 8 steps. And like I said, I can get the answers to everything except the CO3 2- just by starting with the Cheese equation and working through it. So the first step, they write a nice chart. Okay, that's not a problem. We put in our Ka1, that's where we should start anyway. They make the approximation, they get the assumption, they get the concentration for H3O plus and HCO3 minus. They're close to what we would make if we did our Cheese equation. Again, they make all the same assumptions, so we get the same answers. And that number is so small that the starting concentration of the acid remains about the same. So that's great. And I mentioned that down here, we could get those answers. Now, when we need to get this CO3 2-, we have to set up another ice chart, another equilibrium, but it turns out we have the answers to it. We know the H3O plus concentration is essentially the same as it was from the previous step because most of the acid is going to come from that first step that's stronger, so we can just plug that straight in. We can just assume that this step is so weak that it's not going to contribute anything. And then the HCO3 is going to be the same. Then these two are going to cancel each other out because they're going to be the same number. So it turns out that it's approximately equal to Ka2. This is another important observation when you're doing problems like this. The answer to your second dissociation is often, now you'll have to check everything else that's going on in the problem, equal to Ka2. Because as you can see, these two both cancel each other out. Again, it may be a circumstance where something else is going on in your equilibrium expression, and you may have to make some other assumptions, but keep in mind that in this case, and in many cases, that's possible. That's possible. They calculate the OH minus concentration. Again, this is easy, just with the Kw. And then you get the pH 4.03, which is what we had at the very beginning when we plugged them in the Cheese equation. So you can do that and kind of work backward or work around. There's multiple ways to solve these kinds of problems because many times you can just make all the same normal, reasonable assumptions you would have made from the starting point. Now they talk a little bit about bases. Now we already know that bases can use the same equation we've been looking at. We just have to subtract the POH from 14 to get the answer. So we'll set up a base dissociation equation here, and it looks very similar to our acid equation. In fact, it's exactly the same, except it has OH minus in it instead, and a protonated B instead of like what they call an HA. But it's essentially the same theory. We can see that we have these bases, right? And these are considered weak bases. So their conjugate acids are generally, in a lot of cases, they're weaker than they are, right? That would be kind of expected if this thing is going to actually behave as a base. But not every case. Not every case. Sometimes the Ka is actually substantially better, in which case these bases are not, they're not going to be particularly good, right? Anything less than 10 to the minus 7 is not particularly great as a base. So some of these, like ammonia, like that's a very standard weak base, very clearly weak basic. It's about as good of a base as acetic acid is an acid-ish, approximately. Aniline is not a very good base, as you can see. Dimethylamine is a pretty good base. Hydrazine is highly explosive. You wouldn't want to handle that, but it's not a very good base. Hydroxylamine is not a very good base. And methylamine is a pretty decent base. Many of these are amines. They have this NH2 group in the structure, and that's common in organic bases. So let's work this out using the drug codeine, which acts as a base. So it has a Kb of 1.6 by 10 to the minus 6. They gave us a concentration. I plugged this in the Cheese equation, and I got the same answer that the book got. So that was really good. So we were able to get the pH. They want the concentration of all the species present. So the codeine should stay about the same, right, from what we saw in the previous problem. And the protonated codeine and OH minus should have the same concentration, which is the one I get from the cheese equation if I take 10 to the minus 4.36, which is the POH. Remember that to get the pH, I had to subtract that from 14. This is a base, so I should not have an answer of 4. That's an acidic pH. That's the POH. To get the pH, I have to subtract it from 14 and convert it so that I get 9. Now that's a basic pH like it should be, and now we can get all the answers. So we could see that we could do these fairly quickly without setting up any further workout. We will eventually see some problems where we will need a little more explanation to figure out where we're going, but a lot of these problems have the same form, so I want you to be able to check your answers and work these out in a clean and succinct way so that when you go back and you work through each of the steps and you check everything, you've got some basis to start with. So again, they set up an ice chart. We get the same ice chart we've seen before, right? You're always wondering when will this ice chart ever be different, right? There were circumstances where it will be different. And then we work through all of this, and the pH is greater than 7 because it should be, because this is a base, right? When I add a base to water, I make the pH go up. When I add an acid to water, I make the pH go down. That happens all the time. It's just, is it measurable? Is it significant? Is it something, that is enough? But that should happen. Like I should see something that's like an expected answer. If I add a base to something and the pH becomes more acidic, that's just not possible. That doesn't make any sense. So, okay. So what about the relationship between Ka and Kb? So what if I talked about Ka for some acid and Kb for its conjugate base? So it turns out that if I take Ka for an acid and Kb for its conjugate base, now its conjugate base is different only by 1 proton. Remember, this is the same thing we talked about earlier in the presentations back in the 14.1 presentation. So that's what I mean by conjugate. So an acid and its conjugate base, or a base and its conjugate acid, whichever way you want to look at it. If you multiply their K values, you get the Kw for water. This is only true in water. These are Ka and Kb values in water. So just like how temperature can change the value of Ka or Kb, if you use a different solvent aside from water, these Ka and Kb values, they go out the window because they are in different solvents and they behave differently. Like in ammonia, something might be a strong acid in ammonia that is not a strong acid in water, or a strong base in water that's not a strong base in ammonia, and vice versa. Generally, ammonia is more basic, so its stuff is shifted in that direction. But just be aware that sometimes you can have acid and base in different solvents as long as it can support acid-base chemistry. It's a protic solvent. It has protons that can move around, like ammonia, light alcohols, and water. You can set these systems up, and the Bronsted-Lowry theory works the same way, and you just get different numbers for everything. Okay, and like who's a strong acid, who's a weak acid can change. And who's a base, all those things can change. But the general chemistry ideas still work. And this multiplying here will still work. It'll just give you the K for whatever that solvent is. So this gets us the Kw for water. Okay. So this is the equation. If you take Ka times Kb, you get Kw. And that's because what we've learned in the previous chapters is we can add up equations by multiplying their K values. So if we add those together, we end up with the Kw from the little Hess's law little workout they did before there. And because of this, if we take the pKa of an acid and the pKb of its conjugate base, we will get the pKw, which is 14. Again, assuming everything's at 25 degrees Celsius. That's the assumption we have to make, or all the K values start changing. Correct. So this is just another illustration of the same idea, adding those up and remembering that it's at 25 degrees Celsius. Again, so what we can do with this is the kicker right here. We can get Kas from Kbs or Kbs from Kas. And sometimes there are problems that will give you one of these but not the other, and so you'll have to divide Kw by the value to get the other one that you need. Or convert them into pKas or pKbs and subtract them from 14, if that's what you're looking for. So the Kb for trimethylamine is this. Calculate the Ka for the trimethylmonium ion. Okay, so I just need to take Kw and divide it by my Kb, and I'll get my Ka. So that's pretty straightforward. So to get Ka for HCN, they want Kb for the Cn minus, which is its conjugate base. Again, I do the same thing. I can get the conjugate. They want the pKa, I subtract it from 14. There you go. I may have some problems like this on the exam that are this straightforward. If you just know the equations, you can do them. Nothing too complicated here. So let's talk about salts. So salts are the ionic product of some acid-base reaction. So some acid and a base react with each other and they produce some sort of leftover ions that have some properties after the acid and the base cancel each other out. If you have a strong acid and a strong base and you mix them together, you get a neutral solution if you cancel them out completely. That is, you add equimolar amounts of each so that they completely cancel out. The solution will be neutral. That makes sense. If you have a strong acid and a weak base, the leftover components will be acidic. So it will produce an acidic solution, even if you have equimolar amounts of each, even if they cancel out completely. If you have a weak acid and a strong base, you'll end up with a basic solution, even if you add equimolar amounts of each. Let's try to understand why. So if you have neutral solutions, then you have cations from strong bases like lithium, sodium, potassium, or calcium, strontium, barium, these things. And those don't affect pH at all. They have many metal ions are acidic, but these metal ions have no acid-base properties at all. Group 1 metal cations and group 2 cations have no acid-base property whatsoever. They have no appreciable tendency to pick up protons to form hydrides in any way, shape, or form in water. So they don't conversely act to become acidic in any way. Similarly, the anions from strong monoprotic acids like Cl-, Br-, I-, NO3-, and ClO4- do not pick up protons at all. They don't pick up protons. So that means that they don't affect the pH either. So this whole class of ions has no effect. So like sodium chloride does not change the pH. Potassium bromide does not change the pH. Lithium nitrate does not change the pH of a solution because these ions have no tendency whatsoever to pick up protons or hydroxyl ions or anything. So they don't do anything. To yield an acidic solution from a salt, you have to generate something that has an acid-base property itself. So if I use something like ammonium chloride, the chloride ion has no acid-base properties because it was in the list we saw before. But the ammonium ion is an acid. So it reacts to produce this base over here. So this salt, when I put it in water, will have an acid property. The cation is a weak acid, so this will change the pH. So this salt, if it exists, if we had it, would affect the pH. So keep that in mind. Like salts, this doesn't look like it's an acid or a base, but it is because one of the ions is acidic or basic. And how do we know when that happens? Generally, we're going to be looking for something that's obviously the conjugate acid or base of something that we've seen or heard of before or that we'd have to be told. In some contexts, it may not be clear, but keep in mind what we've been told so we can make some recognition, right? Okay. So another thing to keep in mind is that most metal cations, aside from the ones in group 1 and group 2, are acidic in nature. They form these complexes with water, and they end up having the net effect of releasing protons. So these waters become associated with this metal ion, and then it weakens the bonds between the oxygens and these hydrogens so that sometimes a proton can leave. And when that happens, this net effect is that it makes the water acidic. So most metal ions that are not in the strong base conjugate acid list are going to do this. This makes sense because most metal hydroxides are only weakly basic, except for the ones in group 1 and group 2, the strong bases. Other metal hydroxides like aluminum hydroxide and stuff like this are only weakly basic. So it makes sense that if they're not strong bases, if they're weak bases, then their conjugate acids would be acidic. And this is how that happens physically. They talk about how electrons are attracted and this breaks this link. And so one of these becomes a hydroxide ion because it loses one of its protons, and then it goes over here. So aluminum hexahydrate here has a Ka of 1.4 by 10 to the minus 5. much larger than the Kw. So aluminum ions just generally make water acidic. Again, unless they're coupled with something else that could also cancel that out. Salts of aluminum, like aluminum chloride and stuff like that, are acidic salts, and that's what they're called, acidic salts. They're ionic compounds that when they ionize have acid-base characteristics. So they're not obviously acids or bases. They don't have like an H in the structure, but they still can do that, and this is how that process happens. Transition metal cations give acidic solutions, okay? And the higher the charge, typically the more acidic they become. I would say magnesium is not really a good example to put in here because since it's the conjugate acid of what would be a strong base, if it dissociated completely, it's not that great, but it is definitely better than sodium. But these are all kind of bad. Like by comparison, aluminum is a lot better of an acid than any of these other ions listed here. Transition metal cations like zinc 2+, chromium 3+, iron 3+, those are also all acidic. But typically these group 1, group 2 ones are not very acidic. They're sort of the exception to this rule. So they want us to calculate the pH of this. Now this works just like any other acid, so we can use the Cheese equation here to plug all this in. When I do that, I get 2.93, close to 2.92. I actually went back and checked through the book's math when I got that and was like, I actually think maybe the book rounded a little bit differently or forgot to round or something there. The book sometimes does make mistakes like that. I'm not going to hold it against it. This is very minor. But anyway, this helps us set up this equilibrium concentration, and it's relatively straightforward, and it works the same way as all of our other acid-base type problems. Salts that yield basic solutions, right? So something like sodium cyanide, because the cyanide ion, Cn- is basic. Similarly, fluoride ions, like sodium fluoride, is kind of basic. They put that in like a toothpaste. Sodium carbonate, sodium with any of these other ones will all be basic because the cation doesn't do anything, but the anion is a base. Many anions are bases, many cations are acids. This is like one of those kind of general broad things as you're looking through materials. There's an association between those, and it speaks to something a little bit deeper. It'll be a while though before we talk a little more about that, but just something else to think about. Again, we can get the same answer as the text by looking at the salt of sodium cyanide. Using the Ka for HCN, we converted that to get the Kb for the Cn- ion. We plugged all this in together and we're able to solve it and get the correct answer. This is another great example. This might be the kind of thing I might ask on an exam. You just have to identify that the Cn- ion is a base and then use this Ka. So you're using all the processes and equations we've talked about previously. What if you have both, though? This is where it gets complex. What if you have a cation that's acidic and an anion that's basic in the same molecule? Something like ammonium carbonate. Now that might be a little bit difficult. The math out for it would basically involve combining the two equilibria together, but going into this, we need to know the one that's stronger is going to control whether it's acidic or basic. That we should be able to determine from first principles. If the Ka is a bigger number, then the overall solution will be acidic. If the Kb is a bigger number, then the overall solution will be basic. If they're about the same value, then the solution will be about neutral. So we can do that first, and this is probably something we should check first. So we can tell here that because the Kb for CO3 is 6 orders of magnitude bigger than for the ammonium ion, this is probably going to be basic. And so we could estimate its pH by just using the Kb. 6 orders of magnitude is enough that we probably won't even see this contribution at all. If they were close to each other, like I said, it's going to be close to 7, but exactly what it is, we could calculate it. We would just have to combine together the two results, which can be a little bit complicated. We'll kind of like imagine that each one was in there, and then we'd have to put them together individually and come up with an overall answer. To figure out the amount of H plus and OH minus there is, we could estimate that by adding the two together and assuming they cancel each other out, and then whatever the excess amount goes back into my equilibrium. That's essentially mathematically what we would have to do. But we're not going to see any problems that difficult in this course. But just understand in theory you could do it. You will see examples, though, where I ask you whether this solution is acidic or basic. You should be able to figure that out, even if you have one that's an acid and one that's a base in the same solution. You should be able to figure that out. But I won't ask you to do complex problems where you have to actually work out what the pH would be. Because if you can make that determination, I'm satisfied. Because you should always do that when you first look at the problem. Even if you were going to go down the road of calculating what the exact pH was, you do them as two separate problems, and you combine you let the OH and the H3O plus cancel each other out and then get an overall answer. You would still get the same answer. You'd still be determining you'd still be getting that it's an acid or a base. So G.N. Lewis proposes another theory of acids and bases. It's less dependent on a protic solvent. So Bronsted-Lowry theory really depends on having a solution that supports acid-base chemistry, like water, ammonia, the light alcohols, all their protic friends, and they'll call these protic solvents. They have labile protons that move around. So that mediates the exchange, and that's what makes solutions acidic or basic. If we want to move beyond that concept and have an acid-base theory that doesn't rely on any particular solvent class or type, then we need to move into Lewis theory. In Lewis theory, we say that electrons reach out, and that's what we have these arrows flowing. The electrons reach out and they grab protons. Okay, so something that has the electrons is the base, and something that doesn't have the electrons is the acid. So these electrons grab things, right? And this also delves into the concept of nucleophilicity and electrophilicity that end up being very important in an organic chemistry class. Another way to think about a lot of organic reactions is as Lewis acids and bases. They bring that kind of back up again in those classes in the early times when they talk about that. So, and they'll use these arrows in a very similar way. I'm not going to stress that a lot in this class. I just want to introduce you to the basic theory, right? We can use these arrows to indicate the direction of electron movement, which is typically how it's done. In typical electrical systems, right, like when they wire your house, it's like the movement of positive charge, but in chemistry, we draw arrows to indicate the movement of electrons as negative charge. So this way of thinking of it, like this is still a base and this H plus is still an acid, just like it makes sense it would be. But now we have a way to classify them according to the movement of electrons, which again connects it with the concepts of nucleophilicity that you'll encounter in an organic class. All Lewis bases in water are Bronsted-Lowry bases. I would disagree a little bit with the way that the book frames it. There are Lewis bases that can't work in water, but all the ones that work in water are also Bronsted-Lowry bases. And all Bronsted-Lowry bases are all Lewis bases. That is true, completely. Lewis' definition of acid is broad, and you can have acids that are beyond H plus in the Lewis theory as well. Typically, Lewis allows us to not have to worry about a solvent anymore. It's just a reaction now. Whether that reaction takes place mediated with a solvent or not, it still works. But it kind of gets us away from the idea that in Bronsted-Lowry theory, like a solution has a pH, like the water itself, the whole thing does. And a solution is acidic, and it's caused by the addition of the thing that we call the acid. So it's a little more intuitive when you work with water, but when you're working outside of it, Lewis acid-base theory can be really useful when you don't have a mediating solvent. But you can see that this still works even in water, right? We can think of the water as the Lewis base grabbing this metal cation, and multiple waters can grab this cation. And the electrons are the things doing the grabbing. They're able to move, and they can move much faster than protons can move. And in fact, they generally are the things that are moving. It's just a measure of like which way you want to look at it, right? Typically, we want to look at things in terms of movement of electrons because that's actually generally what's moving. But you could also reframe everything as a movement of positive charge, and electrically everything still works, right? So we can get the same answer whether we think about it one way or the other. It's just important to realize. So a lot of these association reactions where things get associated with a metal cation have this kind of theory with Lewis acid base that might make a little more sense and kind of it adds on to what we've talked about previously. So we can see adding NH3 causes this precipitation to happen and yields this ion here. Again, we can look at just generic acid-base chemistry, like with this sulfate ion, which could act as a weak base because its conjugate acid is a weak acid, and we can show how that could happen. We can show how SO3 behaves as an acid because water gets added to it, and that process is a net addition of electrons. Electrons from the water reach out and increase the electron content by going after this center. This is where it gets a little more complicated, because we can say that these electrons are nucleophilic and this sulfur here is electron deficient and it seeks electrons, and there's a lot more complication going on in here that makes more sense in an organic class. But the way they draw these arrows and the kind of thought process of electrons adding into some kind of center to give it more electrons, and then the molecule kind of rearranging through a variety of additional steps, is a thought that you should keep in mind for a class like that. This is sort of the classic Lewis acid base, the addition reaction of this boron trifluoride with ammonia. The boron and nitrogen have an interesting relationship because together they have the same electron content as two carbon atoms. And so they're able to make pretty strong bonds with each other. Like nitrogen typically has 2 extra electrons and the boron has 2 fewer electrons. So coming together, they're able to form really strong covalent relationships, which they call this an adduct, a product where they add together and form one unit that stabilizes the whole system. Typically, this boron trifluoride is not very stable. Ammonia is pretty stable, but the ammonia's extra electrons stabilize the boron trifluoride. Another way to think about that. So they ask us to identify the Lewis acid and the Lewis base. Generally, this is pretty straightforward. If we can identify something as potentially acidic, right? So the OH minus is the negative thing, and generally that thing is the base, because we know that OH minus is a Bronsted-Lowry base. It's probably the base here. And so it makes sense that it adds its electrons into carbon dioxide to produce this bicarbonate here. So keep this in mind. You won't have to draw anything like this on the exam. I'm not going to ask you to do anything like that. But I might ask you to identify them, and that I think you could do without having to do this additional drawing. Same thing here. This is the base. It adds to the acid. And the same thing here. The metal ion is the acid, and these CNs are bases, and they form a Lewis adduct. All right, so that is the end of our Chapter 14 presentations. I hope you all enjoyed the presentation, and then we'll be moving on to Chapter 15 in the next one. Thanks so much. Bye-bye.